Astronomers have detected an unusual pattern coming from the interstellar object 3I Atlas, a 16.16-hour pulse that causes its brightness to rise and fall with surprising precision. The signal appears tied to rhythmic jets of gas released as the object rotates, creating a clear heartbeat not commonly seen in comets. With 3I Atlas approaching its closest pass by Earth, new observations are revealing details that scientists are still working to interpret. In this video, we will break down the discovery, the science behind it, and what researchers expect next. Let's get started. The first indication that 3I Atlas was behaving unusually came from repeated brightness measurements. Instead of fluctuating irregularly, which is typical for comets as their activity changes, the object showed a consistent rise and fall in brightness every 16.16 hours. Multiple observatories confirmed the same timing, making it clear that this was not a measurement error or a temporary outburst. The pattern immediately pointed to rotation. Comets brighten when certain icy regions on their surfaces face the sun and sublimate, releasing gas and dust. This process often produces irregular variations, but in this case, the changes were both sharp and highly regular. The simplest explanation was that 3I Atlas rotates once every 16.16 hours, exposing the same active regions to sunlight during each cycle. Further observations revealed jets of gas and dust erupting in bursts that match the brightness rhythm. Each active region released material rapidly when warmed, producing jets that traveled close to 1,000 miles per hour. Although jets are common in comets, what made this case distinctive was how closely the activity aligned with the rotation period. Rather than chaotic or scattered eruptions, 3I Atlas showed a repeatable sequence of activity that produced a clean, measurable signal. Another noteworthy aspect was the behavior of the coma, the vast cloud of dust and gas surrounding the nucleus. Most of a comet's visible brightness comes from this coma, not from the solid core itself. Because the coma is diffuse and constantly expanding, it usually responds in a broad, irregular way to new material. Yet the brightness of 3I Atlas shifted in a synchronized pattern that mirrored the rotational jets. This coherence suggests that the jets may be strong enough, or the coma structured enough, to produce detectable pulses before the material disperses. As 3I Atlas approaches its closest pass to Earth, the jets have become easier to monitor, allowing scientists to track how the heartbeat changes with distance from the sun. So far, the cycle has remained stable, reinforcing the idea that the rotational pattern and jet locations are well defined. The discovery phase has therefore provided a consistent picture, a rotating interstellar object with active regions that heat, sublimate, and brighten the coma in a repeating sequence. While the mechanism is rooted in familiar comet physics, the clarity of the heartbeat has set 3I Atlas apart from typical solar system comets. One reason 3I Atlas has drawn significant attention is its status as an interstellar object. Material from outside our solar system is rare to observe up close, and each visitor can reveal details about the environments in which other planetary systems form. In the case of 3I Atlas, early spectroscopy showed that the coma contains an unusually high ratio of carbon dioxide relative to water, which differs from many solar system comets. This composition suggests that the object may have originated in a colder region, or under different chemical conditions, than those that shaped our own comet populations. Understanding the 16.16-hour heartbeat adds another layer to the scientific importance of the object. The leading explanation is that localized pockets of volatile ices on the surface sublimate when exposed to sunlight during rotation. This model accounts for the timing and intensity of the jets and aligns with what is known about comet activity. But in 3I Atlas, the effect is more pronounced and more stable than in typical comets. This gives researchers a rare opportunity to test how well existing models of sublimation, jet formation, and thermal behavior apply to interstellar material. A central question concerns the coma's synchronized response, since nearly all observed light comes from the coma rather than the nucleus. The clean pulse implies that material injected during each jet burst influences the coma quickly and significantly. Some scientists point out that this level of coherence is not straightforward to explain using standard models, which usually treat the coma as a highly dynamic, rapidly dispersing cloud. Studying this behavior could refine understanding of how dust and gas propagate through a comet's immediate environment. Alternative interpretations have been proposed, though they remain within scientific bounds rather than speculative extremes. Some hypotheses explore whether layered ices could create repeated sublimation phases, or whether internal thermal differences could lead to periodic outgassing. Others suggest that the nucleus might have an unusual shape or topography that channels the jets in a repeatable direction. The heartbeat also raises the possibility that interstellar comets may behave in ways not fully captured by models developed from solar system examples. Since these objects were shaped in entirely different environments, their internal structure, ice layering, and chemical makeup could lead to new patterns of activity. In short, the scientific value lies in the combination of a rare interstellar origin, a clear rotational cycle, and a coma that responds in a surprisingly ordered way. Studying 3I Atlas may help expand existing models of comet physics and improve our understanding of how volatile materials behave across different astrophysical environments. The implications of the heartbeat extend beyond the immediate discovery. Because 3I Atlas carries material formed around another star, observing how its ices react to sunlight provides insight into the diversity of planetary systems. The stable pulse offers a controlled way to examine how interstellar volatiles heat, sublimate, and evolve as the object travels through the inner solar system. Another implication involves rotational mapping. The steady timing allows scientists to test models of how active regions influence a comet's overall activity pattern. As 3I Atlas moves closer to the Sun, changes in pulse strength could reveal how deeper or more volatile layers respond to additional heating. If the heartbeat becomes stronger, it might indicate activation of new surface regions. If it weakens, it may signal depletion of the ice responsible for the jets. Monitoring the object before, during, and after its closest approach will help determine whether the 16.16-hour cycle remains stable under changing solar conditions. This data will refine estimates of the nucleus's rotational properties and may uncover subtleties in how the jets evolve over time. The heartbeat also contributes to broader comet studies. Many comets show brightness variations, but few offer such a clear, repeating signal. Understanding how a coma can preserve and reflect this rhythm could help reinterpret brightness changes in more distant or faint objects where direct imaging is not possible. Future observations will include detailed spectroscopy to track how the composition of the jets changes during each pulse, as well as thermal modeling to study how heat spreads through the surface. Combined, these methods may reveal whether the active regions share similar compositions or represent different layers of the nucleus exposed over time. Lastly, 3I Atlas highlights how interstellar visitors can challenge existing assumptions. As survey telescopes improve, more of these objects will likely be detected, each with its own scientific opportunities. The heartbeat demonstrates that interstellar objects may follow familiar physical principles, while still displaying patterns that refine or extend current models. For now, the focus remains on continuous observation. Whether the pulse strengthens, fades, or shifts will help answer several open questions about the nature of the jets, the structure of the nucleus, and the evolution of interstellar ices under solar heating. Whatever the outcome, 3I Atlas is set to provide valuable data that will influence comet studies for years to come. 3I Atlas. Steady heartbeat offers a rare window into how interstellar material behaves under sunlight. As it nears and passes Earth, every change in its pulse will refine our models of comet activity. For now, it remains one of the most informative interstellar visitors we've ever observed.